Hi, in this video, I'm going to go through the OCR AS-level Chemistry paper. So this is paper 1, and it is the Friday, May the 20th, 2017. Okay. All right, so I've covered the first half of this paper in an earlier video. So this is starting off with the second half. The first question is about S&P block elements. We've got a mass spectrum of magnesium there. Okay, the species causing the peaks in the spectrum are 1+ ions of magnesium. Okay, complete the table below to show the number of protons, neutrons, and electrons in each of the ions. Okay, so magnesium, we need to know from our periodic table, is atomic number 12. So that means it's got 12 protons. So all of the isotopes have 12 protons, of course. The mass is equal to protons plus neutrons. So neutrons is subtract the number of protons from the mass. So 24 minus 12 is 12. 25 minus 12 here is 13, and then 14 neutrons there. Now the number of electrons, okay, magnesium, a neutral magnesium atom, of course, would have 12 electrons, but this is a positive ion, so it's lost one, so this is 11 electrons for each one. So that's that table done. Okay, now the next part of the question, it asks us to calculate the relative atomic mass of the magnesium in this sample. 2-mark question. Okay, so we need to go back to this graph for the data here to do the calculation. Right, so the AR, what you do is you add up together, you do abundance times mass, and that's the sum of them for each isotope. Okay, now the abundance, it's easiest, rather than doing it as percentage, if you do it as a fraction, so i.e. this 78.99% is going to become 0.7899. Okay, so the AR is going to be equal to, let's do it for the 24 isotope. So the mass is 24 times the abundance, 0.7899, plus this for the 25 is 10%, so that's plus 25 times 0.1. Plus for the 26, that's 11.01%. So that's 26 times 0.1101. Right, work that out in a calculator, you get an answer of 24.3. Now I think it asks to give us to will give you answer to 2 decimal places. Okay, so there's 2 decimal places, that is 24.32. Sorry about that. Okay. That's 2 marks. Okay. Now, B and C are ionic compounds of 2 different group 1 elements. Okay. The molar masses in B and C are both about 140. All right. Right, both about 140. Right, let's see what the test has done then. All right, so first of all, if you've got B and C, the 2 compounds dissolved in water, and do test tube tests. B, when you add nitric acid to it, you get bubbles. The bubbles are almost certainly of CO2. So that means B is either a carbonate. Now, if it's a carbonate, they have the formula like that. Or if it's a hydrogen carbonate, the group 1 will be HCO3. Now that is, of course, is because group 1 elements always form a 1+ ion, and the carbonate ion is CO3 2-, and the hydrogen carbonate is HCO3 1-. So let's see, what could that be? An MR of about 140. This carbonate bit, that weighs 60. That's 12 for carbon plus 3 times 6, 60. Okay, so carbonate weighs 60. That obviously is going to weigh 61. Let's just see if it could be the hydrogen carbonate. So the MR is about 140. So if we do 140 minus 61, that gives us 79, doesn't it? Okay. As the AR of X. And if you look, none of the alkali metals have an AR of 79. I think I'll just put them up here. We've got lithium is 7, about 7. Sodium is 23. Potassium is 39.1. And rubidium is 85.5. Well, it can't be. I think we can rule out rubidium from all of these things. Okay, it's not going to be rubidium. It's too heavy. Okay, so forget about that. Could it be potassium? Let's do 2 times 39. That's 78 plus 60. That would give us 138. That's about right. So I think that's what we've got there. We've got potassium carbonate. Potassium carbonate is B. So this question is testing, or do you know how to test for a carbonate? Also, do you know that what's the formula of a group 1 carbonate going to be? Right, now this one with barium chloride, we should know that you always, barium chloride, if you get a white precipitate, after you've acidified it, obviously, yeah, then what you've got, so with C, must contain the sulfate group. What's the formula of a group 2 sulfate going to be? Well, group 1 sulfate, sorry, it's got to be X2SO4. Right, where's 140? Now, a sulfate, I don't think C can be potassium, it'd be too heavy, because the sulfate, well, that's 32 for the sulfur, 32 point something, don't worry about that. And 4 times 16 for the oxygens, 64, so that's 80, right? That bit weighs 80, so that means we have got 140 minus 80. This bit has got to weigh about 40, so that means X has got to have an atomic thing of about 20. Well, sodium has an AR of 23, so I think this one, C, has got to be sodium sulfate. Just to check the atomic, the AR of that, sorry, the MR of sodium sulfate, 2 times 23, 46, plus 32 for the sulfur, plus 64, 142. MR is 142. That's about right. It says it's about 140. Okay, so there's our answers then. We've got potassium carbonate and sodium sulfate. Right, figure 1 shows the first ionization energies for the elements across period 3. Right. So, add a point for the first ionization energy of the element with Z equal to 10. Well, just to show where we are, this is sodium, okay? And that's magnesium and so on. So the one there, that is one before sodium, is neon. Now, where's the first ionization energy? The electron for sodium, I'll just write this down here. Sodium is 1s2, 2s2, 2p6, 3s1. So the first ionization energy for sodium, the electron's coming from 3s. For argon, for neon, sorry, the one before, it's coming from, so it's coming from 2p, the electron, which is way closer to the nucleus than 3s, much higher energy. So the first ionization energy of neon is going to be a lot higher, and a reasonable, it's got to be higher than this one as well. So I think in the mark scheme it says anywhere probably about there. They'll let you get away with that. So that's what it's going to be. The noble gases are always, you find them at the peaks in these graphs, okay? Right. Estimate the energy required to form one sodium gaseous ion from one atom. Right. So the first ionization energy, that's the energy required to remove one electron from 1 mole. And that is, you see there, it's 500 kilojoules per mole. Right, so how many ions have we got in 1 mole? We've got 6 times 10 to the 23. So the energy required to remove it from one atom is going to be 500 kilojoules divided by 6 times 6.022 times 10 to the 23. And that is equal to 8.3 times 10, 8.3 times 10 to the minus 22 kilojoules per ion. Right, it does ask it for two significant figures, so I'm going to get rid of that 0 there. I should say 8.3 times 10 to the minus 22. Okay, right. Move on to the next question then. Explain why the first ionization energies in figure show a general increase across period 3, sodium to argon. That's 3 marks for that. So what we can say here is that as you go across from sodium to argon, the nuclear charge increases. So there's greater attraction to the nucleus, but it's only 1 mark. So that's why it gets harder. The next thing we need to say there is that, but the electron is always being removed from quantum shell 3. So that means the distance to the nucleus and the shielding is about the same. Okay, because distance and shielding obviously affect it, and the nuclear charge increases, but obviously because these are going to be the same for each one, but this is increasing, so it goes up. There's your 3 marks there. Why is this general increase not followed from magnesium to aluminium? Let's look at the chart here. Okay, right, from magnesium to aluminium. Right, for magnesium, right, magnesium has got the electronic structure. I'll just write there at the end bit, Mg is 2p6 3s2. Okay, whereas aluminium, it's 2p6 3s2 3p1. So the first electron in aluminium is being removed from the p subshell, not from the s subshell, and the p subshell is slightly higher in energy. So the electron is slightly easier to remove. The electron is a bit further away from the nucleus. Okay, and the next one. Okay, so that's the end of that question. One about equilibrium now. Methanol can be prepared by reacting carbon monoxide with hydrogen in the presence of a copper catalyst. A reversible reaction there. Use the Boltzmann distribution to explain why the rate of reaction increases in the presence of a catalyst. Okay, provided the axes below, which I haven't. So anyway, and you've got to label those axes. It's 4 marks. You get 2 marks for labeling the axis. So here we've got our graph. They always ask you to label these axes. So along this one is the energy of the particle, okay, of the particles, and this is the number of particles. So the graph is going to look something like this. Right, so we've probably got 2 or 3 marks already for doing that. Now what we need to say there is, well, let's say that this energy here is the activation energy normally, and let's say this is the activation energy with a catalyst. Right, now the only molecules that can react are the ones with greater than activation energy. So without a catalyst, the proportion of molecules is the area under the curve, the red area. That can react with no catalyst, yeah. Whereas with the catalyst, you lower the activation energy, so there's a lot more. It's the area under that area I've just drawn there. So that's the proportion of molecules with a catalyst. It's a far greater proportion of molecules, and so more molecules have the required energy, so the rate of reaction is going to be faster. Okay. Okay, the reaction for the production of methanol in the presence of a copper catalyst is carried out 200 to 300 degrees C. Why does the catalyst reduce energy demand? I think it's quite important to read the question here. Why does it reduce energy demand? Why does it do that? Because we get a reasonable rate of reaction. with a lower temperature. Now, why is that good for the environment? Generating high temperatures usually involves burning fossil fuels. Why is it bad to burn fossil fuels? CO2 is released as a greenhouse gas. Okay, so not really much about equilibrium there, that question. Thanks. Okay, a chemist investigates the equilibrium that produces methanol. Right, so there's the concentration of the reactants and products at equilibrium there, and we want to calculate a numerical value for Kc. Okay, so we've got to do that. So we need to write down the expression for Kc. Like Kc here is going to be equal to the concentration of methanol. Square brackets means the concentration of. There's no number in front of it there, so it's just to the power of 1. Divided by the concentration of carbon monoxide to the power of 1, multiplied by the concentration of hydrogen, and that of course is going to have to be squared. Yeah, okay. So it's a matter of putting those numbers in. They give them here. They give the concentrations. So Kc is equal to 0.26 over carbon monoxide, 0.31, multiplied by 0.24 squared for the hydrogen. Put your numbers into the calculator, and that gives a value of 14.6. Right, 14.6 for me now. So it's the appropriate number of significant figures. We should give it to 3 because these are all given to 3 significant figures. So that's there. And the units of that are actually going to be mole to the minus 2 dm to the 6. It gives you that at the bottom of the question. You don't have to. It doesn't actually for the units. I've chopped that bit off, and it actually there was an error notice. Have you noticed that? Because they had misprinted that. They put mole to the minus 6 dm squared, so they obviously messed that up. But that is the right units, even though they don't ask you for them in that question. Right, ethanoic acid. There is the main acid dissolved in vinegar. It is a weak acid. What is meant by acid and weak acid? So an acid is a proton donor. A weak acid is only a small proportion of the acid molecules donate a proton. Okay. Right, or only a small proportion of them ionize, you can say. Okay, right. Aluminium is reacted with ethanoic acid. The unbalanced equation for the reaction is shown below. Right, and we've got to balance it. Right, we need 3 ethanoate ions here. You can see you've got 3, so we obviously got to put a 3 in front of that. That means we're going to need 3 aluminiums. So that's going to give us how many hydrogens? Well, we're going to lose 3 H's, so that's 1.5 H2. I don't really like using, it's all right using halves, but 1.5 is a bit funny, so let's double everything there. So let's have, sorry, it wouldn't be 3 aluminium, it would be, sorry. Let's double everything. Start again with that. So you want 2 of those, so 2 there. So you want a 6 there, and that is going to give us 3 H2s. Okay, which deduce the element which has been oxidized and which has been reduced. Now, right, let's have a think about fixed oxidation numbers. Hydrogen is always +1 in its compounds, but it's not in its compound there, it's as an element, so that's 0, okay? So hydrogen's got an oxidation number of 0, whereas here it must have an oxidation number of +1. Okay, so the element has changed this from, the hydrogen has gone from +1 to 0. So that's actually been reduced. So something else has been oxidized. It's not the carbons, it's not the oxygens, it's the aluminium. This is aluminium is an element here. So that's going to be, got this the wrong way around, sorry. So the hydrogen has been reduced because the oxidation number has gone down. It's gone from +1 to 0. The aluminium has been oxidized. So it starts off at 0. Now, what's its oxidation number here? Well, aluminium always forms an Al3 plus ion because it's got 3 electrons to lose. Its oxidation number is always +3 when it's in its compound, so that's it. Okay, a student plans to determine the concentration of ethanoic acid in a bottle of vinegar. The student will carry out titration with aqueous barium hydroxide. Okay, so the method is outlined below. So let's draw a little picture. We're going to have a little bottle of vinegar. Okay, and you're going to take 10 centimeters cubed out of that, and you're going to make it up to 250. That's going to go into a volumetric flask. Okay, and then it says here we're going to take out 20. We're going to put that into the burette. Okay, so that we don't take 25 of that out unusually. That goes into the burette. The diluted ethanoic acid. And you titrate that against barium hydroxide in the conical flask here. And we use 25 centimeters cubed of the barium hydroxide. The concentration of the barium hydroxide, they tell us, is 0.045 moles per decimeter cubed. Okay, and so we've got to find out the number of, what does it say? We've got to calculate the concentration of the ethanoic acid in the original vinegar. So in this bottle here, there's quite a few dilutions gone on there. So let's do that. And it tells us the average titer of the ethanoic acid was 25.45 centimeters cubed. Okay, so what can we work out there? Well, we can work out the moles of barium hydroxide because we know the concentration and the volume. So let's do that. Moles BaOH conc times volume, concentration 0.045, volume in dm cubed is 0.025. That gives us a number of moles of 1.125 times 10 to the minus 3. Now, how many moles of ethanoic acid does that correspond to? So how much of ethanoic acid have we got in here? Well, we'll look at the ratio. It's 1 mole of barium. You need 2 moles of ethanoic acid. So let's write down our moles of ethanoic acid. And that's in the titer of 24.45 centimeters cubed. Sorry, 25.45 centimeters cubed. So that's double that. 2 times 1.125 times 10 to the minus 3 is equal to 2.25 times 10 to the minus 3. Now we know the number of moles of ethanoic acid and the volume it's in. So now we can work out the concentration of this ethanoic acid. So let's work out the concentration of the diluted ethanoic acid. Let's do that. So concentration of the diluted acid is equal to moles over volume is equal to, we've got 2.25 times 10 to the minus 3, and the volume is 0.0, is this one here, 0.0 divided by 1,000, so that's 0.02545. That is equal to 0.0884 moles per decimeter cubed. Okay, so let's write that down here. We know the concentration of the diluted vinegar. That's 0.0884 0.084 moles per decimeter cubed. Right, now let's say how much vinegar have we got in this? How much ethanoic acid have we got in there? So let's do moles of ethanoic acid in that column in the volumetric. Moles ethanoic acid in the volumetric. Well, it's going to be conc times volume, so it's 0.0884 multiplied by 250 over 1,000, 0.25. That gives us 0.0221 moles of ethanoic acid. Okay, but look, all of that acid came from 10 centimeters cubed of vinegar. So the final bit of the calculation, now we've got to do the concentration in the vinegar. So the concentration of acid in the vinegar is equal to the moles divided by the volume. So we just said the moles in the 10 centimeters cubed volume of vinegar was 0.0221. That comes from 10 centimeters cubed of vinegar, so that's 10 over 1,000, which is 0.01 dm cubed. So that gives us an answer of 2.21 moles per decimeter cubed. That is the concentration of ethanoic acid in the original vinegar, which to me seems very high. I don't think vinegar is ever anything like as strong as that, but that is the correct answer. Okay. Right. This is a bit of a funny question. Suggest one assumption the student has made that might mean their calculated concentration of ethanoic acid is invalid. Right. What they are, the only thing to say is they're assuming the only acid is ethanoic acid. And there might be other acids in there. Predict with the reason how the experimental result would differ from the actual concentration if the assumption, well, if other acids are there, the concentration of ethanoic acid calculated is way too high. It's going, well, slightly too high or a lot too high. Because not all of the acid in there is ethanoic acid. Presumably there are other acids present in there. Okay, that's a bit of a funny question, that one. Okay. Question about alkenes. The combustion of ethene is shown in the equation below. Explain in terms of bond breaking and forming why a reaction can be exothermic, right? I think there's 2 marks for that. Well, I think, or maybe just 1. I think what you need to say is that breaking bonds requires energy. Making new bonds that releases energy. And then I would say, if the new bonds formed are stronger than the old bonds, and the bonds broken, then the reaction is exothermic. Okay, so most reactions involve breaking some bonds and then making some new ones. And if the ones you make are stronger than the ones you break, it's exo. Right, here is a bond energy calculation then here. It says, right, average bond enthalpies are shown in the table. I'll give you them all. Calculate the bond enthalpy of the CC bond. That's what we've got to do, using the bond enthalpies and this equation here, which I've pasted down again. So they tell us the enthalpy change for this reaction. Okay, so bond enthalpy calculations. I'm going to draw out all the structures, draw the equation out, but I'm going to show the bonds so we don't forget about any bonds which are there. So we've got ethene, double bond, that's one we've got to find out, and then 4 singles to the hydrogens. We've got 3 O2 molecules, the double bond there, and that is going to react to form 2 carbon monoxide, carbon dioxide molecules. So we have a double bonds there between, and also we have got 2 water molecules. Right. Now, when you do a bond enthalpy calculation, what I'd like to do is I put down as a third thing in a Hess's law cycle, I like to put down the atoms, gaseous atoms here. So what we're going to do is, in this limb here, we're going to break every single bond there, okay, and work out the amount of energy we need to break those bonds. And that is going to give us 2 carbon atoms, gaseous, 4 hydrogen atoms, and 6 oxygen atoms. And then we're going to build all of those back up again and form some new bonds to form the products. Okay, so let's see how much. Now this red arrow, let's fill in the arrow of that. What bonds have we got to break? Now breaking bonds is endothermic, so that means we are going to give that a positive value. What bonds are we breaking there? Well, we're breaking 4 carbon hydrogen bonds, so that's going to be 4 times 413. We're breaking 3 oxygen-oxygen double bonds, so 3 times 498. And we're breaking this carbon-carbon double bond. Let's call that X. That's what we're going to find out. Let's add all that up together. That's going to be a positive number. It's endothermic. We're breaking those bonds. So that's 3146 plus X. X is the bond enthalpy of the carbon-carbon double bond. Right, on the green arrow then, what we're doing, we're making, well, two carbon dioxide molecules. We're making 4 carbon-oxygen bonds. So that's 4 times 805. And we're making 4 bonds of that, 4 times 464. So let's add all that up together, and that's all going to be negative. Don't forget, I should put minuses in there because we're forming those bonds. That's minus 5,076 kilojoules for that. Okay, so using Hess's law, we can say that the blue arrow here, delta H, is equal to the enthalpy change on the red arrow plus the enthalpy change on the green arrow. Okay, so let's write that in. So delta H we know is minus 1318. That's equal to the red arrow, we've got 3146 plus X. Follow the green arrow, minus 5076. So let's just put the numbers into that. We get minus 113 is equal to, you just rationalize that, X minus 1930. Rearrange that, we get X is equal to plus 612. Okay, so our final answer, we will say that the bond enthalpy of CC, we don't usually give it a sign, we just give it a number, is 6112 kilojoules per mole. And it shows much working out as possible there, because if you get the wrong answer, and your working isn't easy to follow, you probably end up getting 0 marks for that instead of the 3 marks that are going for it. Okay. Right, now here's an ideal gas calculation for 5 marks. Alkene D is a liquid but can be easily vaporized. When it's vaporized, okay, this temperature 3, so that's 100 degrees C, isn't it? Produces a certain amount of gas, and we've got to determine the molar mass from that. Well, how do we do that? We need 2 equations. We need the ideal gas equation, PV is equal to nRT. From that, we're going to work out the number of moles of gas we've got in there, okay? So N is the number of moles, so N is equal to, rearrange PV over RT. Then we're going to use moles is equal to mass over MR, the molar mass, okay? So the molar mass, MR, rearrange, is equal to mass divided by the number of moles, which is, of course, is N, that we have found out in this equation here. Okay, so let's do that. Now with the ideal gas equation, you've just got to be really careful with units. So pressure has got to be measured in pascals, not in kilopascals. So N is equal to 101 kilopascals. That's 101 times 10 to the 3 pascals. Volume, this is where everyone forgets, so we're really careful here. That's right. There's 8 volume is equal to 82.5 centimeters cubed, but we've got to measure it in meters cubed, and 1 meter cubed is equal to 1,000,000 centimeters cubed. So this volume you've got of 82.5 centimeters cubed is actually equal to 82.5 divided by 1,000,000 times, okay, meters cubed. Let's put that in there. So multiplied by 82.5 times 10 to the minus 6. People seem to forget there's a lot of centimeters cubed in 1 meter cubed, more than you probably think before if you didn't think about it. 1,000,000, right? R, universal gas constant we're given is 8.31. The temperature should be in Kelvin. It's already given in Kelvin. We don't need to convert it. 373. We get a value of N there of 2.68 times 10 to the minus 3 moles. Okay, now we can put that into this equation. Right, so we want MR is equal to the mass, which is 0.1881, divided by the number of moles, which is this here, 2.688 times 10 to the minus 3. And that gives us an answer of 69.97. Now, what about significant figures? Well, the least accurate data is given to 3, so we should only give it to 3. So that is going to be equal to 70.0 grams per mole. The molar mass of the gas. Right, now I think, okay, it was an alkene. Okay, it's probably going to ask us what that alkene is. I think it does. I haven't pasted it. Well, what is that alkene likely to be? Okay, it is likely to be, well, let's see, an alkene is going to have the formula CnH2n, and the MR is going to be 70. So if we have 6, that's going to be too big. 6 times 12 is 70, that's 5. So if we have C5H10, that would be perfect. That would be have an MR of 70. So we've what there is pentene, and that is the last question on the paper.